So let's go over to page 481, please. You do need to know these definitions. I'm going to tell you right now, you'll have to do definitions on your test. So, shouldn't be hard though. Kinetics, just the study of chemical reaction rates. Catalyst increases the reaction without being used up. Heterogeneous catalyst is just a different phase in the reactants, and the homogeneous catalyst is the same phase as the reactants. Not hard. So you tell me, what are the units for reaction rate? What are the units for the reaction rate? That's the big R. Here, let's just... Yep, very good. Remember, you got to know this. So when they ask what are the units for the rate, they're asking for this. So you guys said, what was it? Molarity per second. For those of you that are thinking, I don't know where they got that, I want you to just flip the page over to page 482. And on number 14, you see the trial there with all the experimental data. Go to the far right-hand side, which shows you the instantaneous rate. And do you see the units? That is R. That is R. Okay? Does everybody see that? All the way over to the right, R is always given to us in molarity per second. Okay? In case you haven't seen that yet. Want to make sure you got that. Okay, flip back. Okay, number 3. The reaction rate for a particular reaction can be defined in 2 ways, and it gives us the rate equals the change of SO2 concentration over the change in time, or the rate equals the negative change in SO3 concentration over the change in time. Which is the reactant? And Maggie can't answer. Everybody else has to pitch in now. So you, come on, tell me. Which one is the reactant? Good, it's got to be SO3. Somebody other than Luke, tell me why. Why does the answer have to be SO3? Because it's negative. And remember, the reactants are getting smaller while the products are getting larger, and therefore you have to put the negative there to keep the rate positive. How we doing? These kind of questions are on the test. I want to make sure you're okay with the logic. Okay? So if you have a question or you're sitting there going, I just don't get it. It's okay, tell me now. Not later. Now would be good. Number 4, during a kinetics study, a student measures the rate of a chemical reaction to be that. His notes say that he measured the concentration of the product at 1 second, but the concentration at that time is smudged and unreadable. However, you can read that he next measured the concentration of a product at 5 seconds, and it's 2.8 molar. What is the concentration at 1 second? Now, that might sound really scary, but it's not. Because remember, all you're dealing with here is R equals the change in the concentration, right, over the change in time. And we're given the rate of the overall rate, so we can plug that in, equals, and then we're looking for the initial concentration, which I'm just going to make X, okay, minus the final concentration, which is, final minus the initial, shame on me. Okay, so it's 2.8 molar, that's your final, minus X, which is the initial, that's what we're trying to find. And then we have it at 5 seconds, minus, which is the final, minus 1 second, which is the initial, and you're just going to solve for X, aren't you? And everybody here can do that. You just take and multiply this by 4, and then you're going to, I added the X to both sides and then subtract it that way. That's just my way. But anyway, you guys would come out with an answer. Now, the actual answer that comes out is 1.44 molar, but you can't use that answer, can you? When you get this, X equals 1.44 molar, you can't use that. Tell me why. Significant figures. I have to have 2 significant figures, don't I? So my answer has to be 1.4 molar. Right? And if you actually plug it back in there, it doesn't work perfectly, but that's because we've ripped off a significant figure. But you just answer it the way you're supposed to. Okay? All right. Let's see. Number 5, a single crystal of Cupric sulfate, that's copper, you know that, is reacted with sodium hydroxide to make cupric hydroxide. In a second experiment, a cupric sulfate crystal of the same mass is crushed into a powder and reacted with the same amount of sodium hydroxide at the same concentration and temperature. Which reaction has the fastest rate? Good. The powder, the crushed one. Very good. Thank you. Number 6, the rate of the reaction is measured at 50 degrees Celsius. If the experiment is later done at 25 degrees Celsius with the same reaction at the same concentration, will its rate be faster or slower than the original experiment? Slower, because it's 25 degrees cooler, and therefore it's going to be much slower. Number 7, a reaction is allowed to proceed for a while, and then its rate is measured. More of one reactant is put into the vessel, increasing the concentration of that reaction, of that reactant. The rate is measured again right away. How will the two rates compare? The second one will be faster, but there's a caveat attached to that. What would be the caveat attached to that?
What if the reactant was not the one that was added?
Well, what I said, what if the reactant order was 0 on the one that was added? Because you guys have already dealt with zeros as order of a certain reactant, and if that is the case, you can add all you want and it doesn't change the reaction, does it? And yet he doesn't deal with that in the answer key. But I actually wrote there, I take these and then I look at the answers. So I just want you to know that so I can kind of feel where you guys are feeling, okay? And it says, I put the second one should be higher if the order of that reaction is not 0. That's what I actually put there, because that would be the caveat that would keep that from happening, okay? Number 8, fill in the blank. In order for reactants to produce products, they must participate in an effective collision. Let's see. Number 9, how does collision theory explain why reaction rate increases with increasing temperature and increasing reactant concentration? If you have more collisions, you're going to have more effective collisions, right? Okay. Number 10, the rate equation for a reaction is determined to be the rate equals K, a to the second B. What is the order of the reaction with respect to A?
2.
2. Okay. B, what is the order with respect to reactant B? 1. Okay, this table has to answer the next 3 questions. Okay, nobody else speak, all right? C, what is the overall order of the reaction? Good. Elizabeth says she wanted to get out of there easy and fast. Number 4, what is the unit of the rate constant? Really? Okay, come on, man. Come on, man. Come on, man. Remember, that's good. I'm glad this came up because you've got to be able to do this for your test. Remember, R is always that. Always that. The rate constant, you have to determine it. Now watch up here for a minute, Luch. Let's say that the order of these ended up multiplying together to be 4. Okay? You're always, to find this, going to have to swing this over here, so it's going to end up being this. So when I take this off, this is going to be 3, so that's going to be 1 over molar cubed S, right? Let's say this was a 2. We're going to swing it under here, so now we're going to have, so that's going to give me 1 over MS, correct? Do you see it? So you determine this by just MS, and then you're going to divide over here whatever the order is. So this is always going to be 1 over this 1 down, okay, to the S. It's always going to be that. But you can figure it out this way. Don't anybody else answer. So Luch, look at that one. We've determined that the overall order of this one is cubed. So we're gonna do this one. So what's K have to be?
K equals M over MS2.
Okay, M over M cubed S, right? That's when you swing it over. Now what is this going to do?
Cross out.
Right. So what's that going to be?
1 over MS2.
M squared S.
Oh,
you meant that. You just didn't say that. Okay, so you meant the right thing. Okay, that's cool. I do that stuff all the time. All right, so we good? So you see how you get those now. Sean, how we doing? Yes? You fellas okay? You okay? All right. How are we doing back there? We're good. Okay. This chapter's not bad, but it's easy to get confused, in my opinion. So, all right, let's see. Number 11, the rate constant for a reaction is that. What is the overall order of the reaction? Now, hang on just a sec. Let's let Luch do this. No. Come on, Luch. Come on. Luch, K equals this.
Okay.
What does the overall order of the reaction have to be? 1 up from that, right? So what would it be? 4, exactly. It's not hard, is it? You just got to know what you're doing. Wow, does that sound like chemistry? I should make a little recording, huh? It's all a chemistry. You got to know what you're doing. Okay, I feel like Eeyore saying that. Number 12, the rate equation for this reaction, and it gives it there, is R equals KB to the squared. What is the order of the reaction with respect to A? You're not allowed to answer. Somebody else has to. Come on, Laura Lynn, give me that one. 0. It has to be 0 because it disappeared. Thank you. And so the only way it could disappear is it has to be 0, right? If you double the concentration of A, what happens to the reaction? No change. It doesn't change at all. That's why I answered the way I did back on number 7. Because if you add something that has a 0 order, the concentration acts like you haven't added the concentration. It just does nothing to it. There's no change. Okay? Very good. Thank you. Number 13. If a reaction is left to run on its own, what happens to the rate of the reaction as time goes on?
Decrease.
Good. Slows down. It decreases. Okay. We're going to come back to 14 and 15. Let's go to... No, let's do 14 because it seems to me that's where it got weird. So... It's one of my husband's favorite lines. It got weird. So, all right. So we're going to do the rate equation. So the first thing you do is you go R equals K, and then you look for A, and it's going to be ClO2 to the X. And then it's going to be OH minus, I saw it that time, Brittany. Thanks for before. I saw it that time. And that's to the Y. Okay, so now we're going to figure out the X and the Y. So first, let's find X. So, and remember, I'm going to do it my way, and you're welcome to do it his way, but I want to find X first. And so I'm going to hold OH minus steady at 1 and 2. Now, notice when you go to 1 and 2, the first one is 0.060 molar, and the second one is 0.020 molar. Normally, he goes from a smaller one to a larger one. Here, he's got it reversed. And so if you try to do it this way, it gets confusing. But if you go ahead and just flip-flop them, it's no problem. So what do I have to multiply that by to get to that? 3. So I've got 3 to the X equals, and I'm going to go over here, and I'm going to take the second one. So the second one is 0.00276 molar per second. And then the first one is 0.0248 molar per second. Okay? Once again, I'm going to take this and divide it, that and divide it by that. Or what do I have to multiply that by to get to that? And what is the answer going to be? Good, it's going to be 3. And I would just put it in your calculator and it'll give you 3. So what does X have to be? To make that true, it's got to be 1. So I'm just going to take that away, okay? And then the rest of it is pretty straightforward. So if you get in a jam and it's not going up, like this one, just flip-flop it. That's all. And then the next one, we want to see where this is held constant, because we're going to try to find Y. And that's held constant on 2 and 3. So we look at 2, and it goes from 0.030 molar to 0.090 molar. So what do I multiply that by to get to that? 3. Whoops. 3 to the Y equals, and then I'm going to go to the far right, and I go from 0.00276 to 0.00828. What do I multiply that by to get there? Yes. So it's going to be a 1 again, isn't it? Right? That first one was a 2. I did something wrong.
It was 3x and 9.
Oh, it was 3x and 9. We didn't actually do it. Yeah, it should have been a 2. So that should have been a 2. Okay. Why didn't somebody say something?
I was sitting here confused, but because on number 14 for X, I actually got like 8.98.
You know what?
Yeah,
For
the
one of
problem
the
is
things.
the zeros. Is it 0.0?
Right, and you have to-
And 0.00.
Right, and you actually have to do it. Let's go back and do CL again. CL we used 1 and 2, and we said that 0.060 molar was one of them, and 0.020 molar was another. Then if you go to the far right, you have 0.0248 molar per second, and you have 0.00276 molar per second. Okay, and we flip-flopped them. So well, basically you could divide them just the way they are. So you can go 0.06 divided by 0.02, and you know that's 3. And this is going to be to the x equals, and then you have 0.0248 divided by 0.00276 equals, and that's going to give you 9. It comes out 0.89855. It's 9. Okay? So that we know is 2, and that got a 2. And then when we did the other part, we ended up with a 1 because it was 3 to the y equals 3. So that was going to be a 1, isn't it?
So it's okay to round?
Oh, you have to. Absolutely. Absolutely. And so, because remember, they're measuring concentrations. How perfectly are they going to be able to measure a concentration? You know, think about it. And so then I personally always just grab the first line, and if you shove in the first line on everything, you're going to end up with a K that is 230. And Luch, I want to ask you what K's units are. K is a 230. And it's going to be 1 over m something s. What's the m something going to be? What's the order? Good. The order's 3, so it's going to be a 2. Very good. Very good. Okay. All right. So are you guys okay with those? It's work, though. It's just work. But it's not too hard. Number 15, use the data in the table below to determine the rate equation, including the rate constant for the following reaction. Okay, so R equals K C3H6O X and I2 Y. So we know that the rate of this to the y equals whatever this is. Trial 1 to 2, this would be 2. But trial 1 to 2 on the far right, this is a 1. So y zeroes out on us. It's got to be a 0 to make it a 1. So that disappears, doesn't it? And then let's do this one. We have to find places, trial 2 and 3, I was held constant. This would be from trial 2 to trial 3 would be times 2, the x, and you go over to the far right, and that would be times 2. And so that would be a 1. So we're going to leave this guy here and just take that away, and that would be a 1. And then I'm going to plug in the first trial. So I'm going to go 376 m over s equals, we're trying to determine k, and I'm going to put in 0.0010 molar, and that's a 1, so I'm not going to do anything there. And so when I solve for that, that gives me a k of 3.8 times 10 to the 5th, 1 over molar s. So now I'm going to rewrite this as R equals 3.8 times 10 to the 5th, 1 over molar s, seconds, and then C3H6O. And that would be your final answer. 16. At 25 degrees Celsius, the rate constant of reaction A is 824 that. The rate constant of B is 4,260 that at the same temperature. And finally, the rate constant of C is 15 that. Which reaction has the highest activation energy? Now remember, the higher the activation energy, the lower the rate constant. So which one has the highest activation energy? C, very good. That's got the lowest rate constant. Which has the lowest activation energy? B, because it has the highest rate constant. Very good. 17, consider reaction A discussed in the previous problem. A series of experiments at a different temperature indicates that the rate constant is 0.501 that. Were the experiments run at a temperature higher, above or below 25 degrees? Come on, guys.
Lower.
Lower, so it's going to be below because it's a lower rate constant, so we've lowered everything, right? It's got to be a lower temperature. 18, there are two different catalysts that can be used for a particular reaction. The first catalyst increases the rate by a factor of 10, while the second increases the rate by a factor of 100. If the reaction is exothermic, draw the reaction coordinates that represent the original, the reaction, and the first catalyst and the second catalyst. So if you did that, you'd have an exothermic reaction, okay? The second one, you lowered that by some, and it should start and finish at the same place, just so you know. And the third one, you lowered it by 100. And that is very touchy-feely, you know, so don't think it's going to be perfect and look just like mine. It's just the idea, okay? Because mine's very touchy-feely. Who we kidding? Okay. Number 20, let's start there. Solid platinum can catalyze the decomposition of ethanol vapors. Solid platinum, ethanol vapors. Is it heterogeneous or homogeneous? Okay, heterogeneous because it's different state or phase than the reactants. Number 21, give the following reaction mechanism, and we're supposed to determine what the catalyst is and what the reaction is. Okay, now, first we want to see the catalyst. What goes in the exact same way it comes out?
Bromine.
Yep, Br, bromine, right. Okay, so this goes in exactly the same way as it comes out, correct? So that's our catalyst. So our catalyst is 2Br.
It's actually a negative one.
Thank you. You know, I wondered about that. Because it should be, yep, it should be Br2 otherwise. Yeah, because remember it's a halogen. It's in group 7, so there should be 2 of them like chlorine or oxygen or one of those. Thank you very much. Okay, so that's our catalyst. Now we're looking at who's going in that's also being pulled out or going out that's also being pulled in. And so this, now this is, but this, look, here's water. Nope, that stays. This guy, there you go. He's coming out and he's going in, isn't he? Right? Coming out and going in. So we've got 2H2O2 aqueous yields 2 waters plus O2 gas. Well, we know that equation, don't we? Yeah. But we just figured it out the way he told us to. 22. A catalyst speeds up a reaction without changing the mechanism of reaction. Is it homogeneous or heterogeneous? Heterogeneous. If it doesn't actually get involved, it's heterogeneous.